Okay, in this video, I want to show you first of all why it's important to label your histogram, not only with labels, but also with a title. So this is a histogram that I made. I used the Windows Paint program, and I don't know if you can tell, but that's a really nice histogram. I kind of have some skill there with the Windows Paint program. You can see I just love how I outlined each bar here with a nice dark outline, and then I kind of got the charcoal gray thing going on the inside. Isn't that nice? It's beautiful, isn't it? Like a perfect histogram. I even copied and pasted kind of the width of the bars along there so they would just be perfect there. It's a wonderful histogram, isn't it? Except for it doesn't tell us anything. Okay? So it's just like a picture shape. It doesn't convey any information. Okay? Now oftentimes labels can help here, and so I have another the same one here, and I put the labels on. So down here, these are years, right, and the frequencies, and so I guess you can see that there's kind of a lot of observations that occurred between 15 and 20 years, and some between 20 and 25, some between 10 and 15, some between 5 and 10, not so much there. And so, but do you see, even with these labels, it doesn't convey any information, right? So what is this lacking? And the answer is it's lacking a title. You actually need a title on there that tells the person what the histogram is all about. And so titles are very, very important. So now with the title here, this is years of practice for local medical doctors. And so what you can see here then is, for example, the number of local medical doctors that have practiced between 15 and 20 years is like a little more than 50, and so on. So can you, with this title, interpret what this graph says? And the answer is yes, you can. The title is the key that unlocked the information in this graph. Without the title, the graph, even, no matter how nicely you did the graph, without the title, the graph did not convey any information. And so so the titles are very, very important. And I do take a point off if you do the histogram. Usually the histogram is worth 5 points, and I take a point off if you forget the title, and another point off if you forget labels. And usually frequency is okay. At the time I made this, I just required my students to put frequency, but it would have been even better to write number of local medical doctors or number of doctors alongside here, because then that makes even more clear what the graph is saying. These are the number of years. This is the number of doctors that have practiced that many years. So titles and labels are very, very important. Okay? Now in this video, let me share one other thing. And that is, I want to talk about the shape of a data set. So basically, we say that a data set can have 3 possible shapes. And this really only applies for quantitative data. For qualitative data, this does not apply. So, but a quantitative data set, it can actually have many, many possible shapes, but we say there's 3 overall shapes, and then the other shapes, it can be further classified into other shapes. But the 3 most important kind of overall shapes is a symmetrical data set. Symmetrical data set. And this would be a data set that's roughly the same on both sides of the data set. Okay, doesn't have to be perfectly the same, but if it's not noticeably skewed one direction or another, we would say it's symmetrical. Okay, but then you could have a data set that is like right skewed. And what causes the skewness is that there would be an outlier here on the right. So this would be an extreme value on the right. And that would skew the data to the right. So a right skewed data set. So notice on a right skewed data set, you actually get most of the data on the left, because the skewness is not where the data is, it is where the outlier is. So a really good example here would be kind of like if we had all of our incomes down here, and then Bill Gates would be an extreme outlier that lies way over on the right. In fact, it would go further than this. It would probably be over outside to my neighbor's house, right? He is so skewed, and his mean, that mean would like his income would skew the results. So if we found the average income for all of us and we threw in Bill Gates, the average income would be like $1 billion each. It'd be like adding all our money together and then evenly distributing it, and we'd each be making $1 billion, right? And so that really skews the results, because if we average just ours, we would have your normal income. Throw in Bill Gates, that skews the data to the right. The mean, standard deviation, they become much bigger than they would otherwise be. Okay, so the other side you have would be a left skewed data set, and this would be an outlier here on the left, skewing the data to the left. So you have right skewed with outliers on the right, left skewed would have outliers on the left. So let me just give a quick example for each one. The common ones that you see, they say that people's heights are symmetrical. Usually you got the average person in the middle, and then as you get taller and taller, shorter and shorter, the frequencies go down, and it kind of tapers off evenly on both sides, and it's pretty symmetrical. Okay, so people's heights are symmetrical. People's weights are not symmetrical. That would probably be right skewed. Okay, because you'd have some people that are heavier, and that would skew the data to the right. Okay, well, for a right skewed data set, the most common one used as an example would be incomes. And that's the example I gave earlier, because you know, the majority of people make your average income. There's a few Bill Gates out there that are skewing the data to the right. And then for a left skewed data set, common example would be age at death. For humans, because majority of people live your average lifespan, give or take a few years, but there are a few people that die through accident or illness. They die at a younger age, and that would be over on the left, and they would be outliers that would skew the data to the left. So those are three common examples. And so what I usually do is, if I have you make a frequency distribution table and histogram for numerical data, I usually want you to state the shape, and when I say that, I just mean, is it roughly symmetrical, roughly the same on both sides, or is it skewed one direction or the other? And so the college tuitions, they would have been right skewed. You have those really high tuitions that skew the data to the right. The example we just did, boy, that's really hard to say, but I would say that it's kind of roughly symmetrical. It's just missing a little bit here. If there were a few more here in 17, then I would have said it was perfectly symmetrical. Not perfectly. Well, actually, yeah, if there were 4 more here in 17, it would have been perfectly symmetrical. But I would say kind of roughly symmetrical, though that is kind of a weird shape. Okay? The qualitative data here, we don't give it a shape because we can arrange this however we want. So I don't say that this is right skewed or anything like that. Okay, the shape of the data is just reserved for quantitative data sets. So okay, so now in the next couple videos we're going to do grouped frequency distributions.